In chemistry, a polyyne is any organic compound with alternating, single and triple bonds, that is, a series of consecutive alkanes, N with N greater than 1. The simplest example is diacetylene or buta 3-diner, H-CC-CC-H. These compounds have also been called oligoene, or carbenoids after carbene infinity, the hypothetical allotrope of carbon that would be the ultimate member of the series. The synthesis of this substance has been claimed several times since the 1960s, but those reports have been disputed. Indeed, the substances identified as short chains of carbene in many early organic synthesis attempts would be called polyyne today. Polyyne are distinct from polyacetylenes, polymers formerly obtained by polymerization of acetylenes. The backbones of polyacetylenes have alternating single and double bonds N. In biochemistry and plant biology, polyacetylene is routinely used to describe naturally occurring polyyne and related species. Along with cumulinous, polyyne are distinguished from other organic chains by their rigidity, which makes them promising for molecular nanotechnology. Polyyne have been detected in interstellar molecular clouds where hydrogen is scarce. Synthesis. The first reported synthesis of polyyne was performed in 1869 by Carl Glaser, who observed that copper phenylacetylide undergoes oxidative dimerization in the presence of air to produce diphenylbutadiene. Using various techniques, polyyne HNH with N up to 4 or 5 were synthesized during the 1950s. Around 1971, R. Johnson and D. R. M. Walton developed the use of end caps of the form -3, where R was usually an ethyl group, to protect the polyyne chain during the chain doubling reaction using Hayes catalyst TMEDA complex. With that technique they were able to obtain polyyne like A3CMSIET3 with M up to 8 in pure state, and with M up to 16 in solution. Alkanes with the formula HNH and N from 2 to 6 can be detected in the decomposition products of partially oxidized copper acetylide 2C2-2 by hydrochloric acid. A carbonaceous residue left by the decomposition also has the spectral signature of N chains. Organometallic polyyne capped with metal complexes are well characterized. To date, the most intense research has concerned rhenium, ruthenium, iron, platinum, palladium, and cobalt complexes. Stability. Long polyyne chains are said to be inherently unstable in bulk because they can cross-link with each other in an exothermal reaction. Explosions are a real hazard in this area of research. They can be fairly stable, even against moisture and oxygen, if they are end-capped with suitable inert groups rather than hydrogen atoms, especially bulky ones that can keep the chains apart. In 1995, the preparation of carbene chains with over 300 carbons was reported using this technique. However, the report has been contested by a claim that the detected molecules were fullerene-like structures rather than long polyyne. A polyyne compound with 10 acetylenic units, with the ends capped by fresh A-type aromatic polyether dendrimers, was isolated and characterized in 2004. As of 2010, the polyyne with the longest chain yet isolated had 22 acetylenic units, end capped with trismethyl groups. Polyyne chains have also been stabilized to heating by co-deposition with silver nanoparticles, and by complexation with a mercury-containing tridentate Lewis acid to form layered adducts. Long polyyne chains encapsulated in double-walled carbon nanotubes have also been shown to be stable. Structure. Synthetic polyyne of the form R-N-R, with N about 8 or more, often have a smoothly curved or helical backbone in the crystalline solid state, presumably due to crystal packing effects. For example, when the cap R is triisopropylsilyl and N is 8. X-ray crystallography of the substance shows the backbone bent by about 25 to 30 degrees in a broad arch. so that each C-CC angle deviates by 3.1 degrees from a straight line. This geometry affords a denser packing, with the bulky cap of an adjacent molecule nested into the concave side of the backbone. As a result, the distance between backbones of neighboring molecules is reduced to about 0.35 to 0.5 nanometers, near the range at which one expects spontaneous cross-linking. The compound is stable indefinitely at low temperature, but decomposes before melting. In contrast, the homologous molecules with n equals 4 or n equals 5 have nearly straight backbones that stay at least 0.5 to 0.7 nanometers apart, and melt without decomposing. Natural occurrence. Biological origins. A wide range of organisms synthesize polyyne. The acetylenic fatty acid is isolated from the root bark of the legume Paramicrolobium caerulum of the showy mistletoe family. The naturally occurring pigment terebrine B has been isolated from the giant ragweed. Devil's Club contains oplopandiol acetate. Dihydromatric area acid is a polyyne obtained from the soldier beetle. Other polyyne from plants include enanthotoxin, cicutoxin, and falcarinol. Polyyne can be found in Apiaceae vegetables like carrot, celery, fennel, parsley and parsnip, where they show cytotoxic activities. Ichthya. There is a genus of plants whose active constituent is a polyyne called Ichthyotherol. This compound is highly toxic to fish and mammals. Ichthyother terminalis leaves have traditionally been used to make poisoned bait by indigenous peoples of the lower Amazon basin. Aliphatic C. polyyne of the falcarinol type were described to act as metabolic modulators and are studied as potential health-promoting nutraceuticals. Interest in these compounds has stimulated research into their preparation by organic synthesis. Many such procedures involve a Kadiot-Chodkovich coupling. In space, the octatetraenol radicals and hexatrienol radicals together with their ions are detected in space where hydrogen is rare. Moreover, there have been claims that polyyne have been found in astronomical impact sites on Earth as part of the mineral chaoite, but this interpretation has been contested. See astrochemistry.